Hello, this is the beginning of Module 2. The cutoff between modules is completely arbitrary in the same way that driving from Ohio to California does force you to stop maybe every 300, 400, 500 miles and just quit, because I think most people kind of don't like to spend all day in the car. I don't blame you. I do entirely too much of that. So, if we're driving from east to west, starting in like Columbus, we've made it as far as St. Louis, did an assignment, took a test, and now we're getting ready to go on I-70 West from St. Louis to, I don't know, Nebraska. I'll have to check my map a little bit more closely. So, more importantly, we have this metaphor of the layered protocol model, which I first explained to you as 2 layers, then 3, then 4, where we began at the top rung of the ladder, which was applications. And Module 2 lets us descend one rung of the ladder from the view of the user, the view of the application, and then we will kind of go to the view of the operating system in the computer. And I think you'll like it. I think it's kind of a breakthrough in reasoning, and it keeps us completely in this duality mode of thinking where it kind of looks like it works one way, except it really doesn't. And that is perhaps the critical thing to take away from this class, and there's a bunch of them. So slide 1 is our outline, and there are 7 slides today. Looks like I got a couple pictures in here. You can download these MP3 modules and listen to them on your personal device. You may play them back at double speed or 150% speed, which makes me less boring perhaps, or at least easier to tolerate. And I print all these things and I scribble on them, and they all fit on one sheet of paper for the most part, if you can print front and back. So we are organized, folks. We're looking at just about 3.5 pages of the Bonaventure book, 67 through kind of part of 70. We are going to rely on a couple sketches that you've mostly seen before. And today's kind of review. But if you've done the first quiz, you know that if you go through these slides with a highlighter and point out the main points, then you're doing great. So, outline on slide number 1 is, these are basically the slide titles. So we'll hit them all in order. And we will create a problem, and then we will collectively, intellectually solve that problem. Then we'll, in Module 2, then we'll kind of we'll identify a subproblem to the main problem, and we will efficiently and effectively solve that as well. So for my thoughtful thinkers, let's get ready. Slide number 2, entitled Top Down. Well, there's top down and bottom up, which kind of semantically, logically kind of sounds like opposites. And there is no settled argument here that we have chosen to begin with applications because it's a comfort zone thing. We are very familiar with apps and realize that some apps are for old people, and someday we will all become old people and there'll be new stuff to annoy us. All right, and so we're starting with apps, and then, we could have just as easily begun with the electronics in the boxes and try to make sense out of this stuff. But we're starting from the big picture and then moving into details gradually, gently. It is the same thing as taken place in a lot of other fields where it's arbitrary. So we get just the details that we need in order to do our thoughtful work. So we'll fill in those details. There's something called Fayol's ladder, which kind of dictates which people of which rank in an organization are allowed to talk to each other. And it's pretty much like the low-ranking people don't get to talk to the bosses in the other division, let alone their own. And then Mr. Taylor, who was part of the manufacturing thinking in the era of Henry Ford, these ideas have been in conflict for 100 years, perhaps, or longer. The other thing is we're like looking at opposites. There's induction and deduction that really, in most of this class doesn't matter much, but deduction is to reason from the general to the specific. It is detail oriented. If it's true for the whole, it must be true for the parts, and that is clearly one way of thinking. And in the technical field, when we do problem solving and then implementation, we are very deductive folks in search of the right details to make things work. Now, on the other hand, I'm a professor type, means I've been in school entirely too long. It was the sport I was good at, kind of as it were. As we move from the specific to the general, we are in fact creating knowledge. And as we move from the specific to the general, we're predicting the future. We're identifying where new uses may become. That is Module 3, and that the book on the inevitable stuff is an exercise in induction. And I think part of the bachelor's level college experience is to improve your deductive skills and to help nurture you to develop inductive skills as many of us step into roles of, that haven't been invented yet. Last thing on this slide, I chose the book and our resources based on these apps, and the apps give us some comfort because we know a lot of the details, and it gives us a little bit of framework for moving forward. Slide number 3, Module 1, the application software takeaway. They're user-facing. Applications are the higher layer. They're layer 5 in the 5-layer model. There's also a 7-layer model. I'm not going to teach it, but the applications are the top-most user-facing 7th layer in the 7-layer model. That's always true. We looked at the web. We looked at email. We looked a little bit at DNS only because in each of those 3 cases, it kind of looks like it works one way, except it's implemented in some completely different approach. That is our duality thing. The other aspect that we should really look at as a takeaway, as a broad conclusion from Module 1, is to divide and conquer. This stuff is all software, and we have to organize it hierarchically in order to understand it, in order for the developers to be in different places at different times, for different organizations, different development teams working on different layers and pieces in this. Today, this module is about the operating system that resides in every user device. It could be iOS or Android or Windows or Mac OS. So the service model approach, the application part is pretty well defined because we download it from the store or we buy it online or something. And the infrastructure is everything else. And the everything else part of infrastructure, we could say it's a black box. We know what goes in, what goes out. Don't really need to know how or care much how it works. But of course, we're ITS 2010 scholars. So we do want to know how that infrastructure works. And so we will progressively divide that into 4 layers. The bottom, which is physics and wires and fiber optics, and we won't get too deep into that. Slide number 4. We've started to get into software organization pretty much by saying that hardware doesn't matter. Hardware is a declining unit cost commodity that we purchase on the basis of its selling price. There's really hardly any difference from this brand to that brand, and the dirty little secret is most of this stuff comes from 2 companies in Taiwan anyway, and so it's at the final assembly time that they actually determine whether it's going to say HP or Dell or Lenovo on the front of it, but that is another class. We're responsible for the terms communication, protocol, service model. Abstraction is our friend because abstraction is the engineering word that allows us to ignore the details that are not relevant to the discussion at hand. It's professional indifference. It's not neglect. Okay, and so in the theoretical approach to software organization, is the TCP/IP layered model, which we introduced visually before, divided into the application, end-to-end, global network, local network, and what I refer to as the raw bits. The bits, the frames, the packets, the segments, and the app itself. And we don't want the app user to really have to know anything about any of this stuff. Now, in practice, we're going to be a little bit more cognizant of where the software runs. I've used the word locus, L-O-C-U-S, for that. Some things reside in the pizza boxes that sit in racks in windowless rooms, in windowless buildings. Some things are on our floor or in our building, and other things run in our personal device. We sometimes use the word stack for that. That's a misuse of that expression, but the software stack. And, as today, we're going to step into a new realm. On to slide number 5. Lord of the Rings, right? One to rule them all. This is the model on the left-hand side. This was the one I really didn't want to get into so much. I had a couple different variations of the thing on the left, which says applications talk to applications, and transport talks to transport, and network talks to network. That is a metaphorical, virtual kind of expression. The reality is, you type a key on the keyboard of your computer or phone or what have you, and it descends vertically on the left-hand side to the point it actually touches a wire and goes across some wire or radio waves or something, and then arises vertically through these separate layered things before it is presented to the user or application at the other end. In the layered model, you must know, and this is just memorization, and you would memorize off the Module 1 slide, perhaps a little better. There are 5 layers. They have numbers, 1, 2, 3, 4, and 5. They have names, and they have descriptions, and they have something called a protocol data unit or a service data unit. And so that's the envelope and the letter inside. And we haven't covered that yet, but just as a heads up, for each of those 5 layers, there's a protocol data unit, then a number and a name, and you'll be comfy with that. I know it. The time sequence diagram I just kind of presented there as a review, because ultimately, to reinforce the idea, we may be downloading War and Peace, which is 1,000 characters long, or make up a number, 400 pages long, but it's actually going to get sent in whatever chunks the network deems as appropriate, which is kind of like 1,000, 1,500 characters at a time. So we can say, I'm checking the book out from the virtual library, and it's going to be transmitted from that virtual library, which actually might be in the Cleveland area in Garfield Heights. We can describe that at some point, to your personal device, and will be presented to you, it will be delivered to you intact, transmitted to you in chunks, and the chunks are of the size determined by the network. So, slide number 6, then 7, then we're done. The original internet had these gigantic boxes, and some really colorful people. Happens to be, they were students. Nobody knows who the professors were, ironically, but the students, many of which went on to have great contributions. At this time, we had this thing depicted to the right is the Internet Message Processor. It kind of did everything. So we had mainframe computers, the likes of which we don't even teach or much talk about, but our major banks, insurance companies, retailers, elements of the U.S. government actually have these mega computers called mainframes. They're actually not as large. They're no larger than any of the picture to your right, but they're a whole lot more expensive than that was. So the original internet devices had no PCs. They had no network connections per se. They had no layer 2. They pretty much had the physical copper wires connecting the boxes in various cities. Various cities were like Boston and San Jose and a handful of cities in between in order to connect them, just the way that we're chopping up our distance into modules. There were nodes in Salt Lake City, Chicagoland, Pittsburgh, I believe, and the East Coast. So what happened, first time people tried to even tap a message out from one mainframe to the next, typed 2 letters and it broke. And so everyone has tried to make light of the outcome, but it was a fail. Tried to type in the word login and LO, and it broke. So it happened that at this point, the Internet's founders, who were graduate students lightly supervised by the U.S. Department of Defense, lightly supervised by their professors, observed a class of problems that could only be solved by information that was held by the endpoints, that none of the intervening machines in the middle of the network could do anything about. The devices that were in the middle, connecting the right coast and the left coast between Boston and San Jose, Stanford, I guess that's Palo Alto, the boxes in the middle were performing a store and forward function and lacked the intelligence to fix what broke. The only place where the intelligence resided in order to ensure proper delivery of messages over arbitrary any length or long distance stuff were the devices at the very end, which is a profound idea. To speak in a metaphors, if you have postal mail, a stamp in an envelope from you to, let's say you're writing your senator in Washington, D.C., it's going to go from wherever you happen to be to the next big city to the next big city and sent, between the big cities and then ultimately delivered. If there is an issue in the content of the letter, the only people who can figure that out are the sender and the receiver. The people in the middle, the boxes in the middle, are just handling envelopes. No, they'll handle envelopes to know if they tear one in half, that they're going to tape it together and send it back to the sender. But if there's a true action upon the message inside the envelope, the only groups that can interpret that are the individual that sent it, postal mail, and perhaps the individual that is receiving it, the recipient. So as it stands, we're going to go in with the condition that we can send anything of any size, including all the big stuff. These DVD images, 2.7 gigabytes, I believe. Messages then would be delivered into fragments. They would be cut up into the maximal size that could be shipped across the network, which means if there's a bunch of parts, we might lose some parts. It might be, some could be damaged. They could be lost. If they are sent in a sequence, it happens that they could show up out of order. And the last on that list on the bullet point at the end of slide 6, because we permit retries, our logic, as I just hinted before, was that if there's an error detected, there's a request for something to be resent. So there may be 2 copies of the same thing. So how about that? We've created an environment, we've allowed the rules to be liberal enough, any size object, unlimited size objects between any 2 locations, they're going to get cut up into parts, and everything that could go wrong will go wrong. So as we turn to slide number 7, and I have this, it's horrible. I'm going to end the unit and not have a solution for you, but that ensures you'll come back for the next unit to listen to this. So when the software developers got together to say, well, what are we going to do with this version of having to coordinate between the 2 far ends to work this out? First thing to do is we're going to create kind of a test dummy solution that doesn't do any of that stuff. It just kind of sits there between the application and the network. And I will depict that in the next slide deck or 2. So there's a featureless version of the layer 4, which is called UDP. Those letters don't mean anything. It's user datagram protocol. It does nothing. It just keeps adjacent layers from touching. And then I will mention that there's a great, big, huge amount of code that runs in your phone and your computer and the servers, etc., that serve to provide the 5 functions of the transmission control protocol, all of which we will justify and explain on the next set of slides. Thanks for listening. Module 2, Unit 2, and we're getting into real networking. This is really important stuff, and it really is going to take the entirety of Module 2 in order to make the points that we need to make. So this is kind of past duality. We come into Module 2, and I'm consistently going to use this pages in a book metaphor, maybe not as consistently as I should have, but I have 2 endpoint devices. By endpoint, it's not computer to computer exactly. It's maybe, your computer browsing to a website or your phone connecting to some service someplace. It's just what we do with everything. All of our apps fall into this client-server mode where there's part of what we're doing running on our device. And I'm being very device neutral. I think a lot of people, I hate to say live through their phones, but their portable is their primary device. In the wide world of work, a lot of people, their primary device is their laptop. For those of us so privileged to have an office to go to, I have an office computer. And so, I think for the vast majority of what I do, because we are a Microsoft Office 365 organization as the faculty and staff of Ohio University, it's my desktop in Athens attached to the Microsoft cloud. Microsoft servers are in the cloud for everything, for my file sharing, for my email, for my calendar, the kind of stuff that kind of professors do. If I worked for a real company and traveled, then I might have my laptop that I took with me everywhere that I went, and kind of sort of doing the same thing, either attaching back to the headquarters or attaching to a third party again, back to the Office 365 stuff. So, we're going to allow anything of any size to be sent from anywhere we want to go. That is simply the rule, and that doesn't matter if we're doing this through our phones or while traveling or at our workplace or at our home, because I think these days we do all of the above. Any size, any place, and things will be divided into units that are sufficiently small to get passed across the network. In 2019, 2020, maybe that was a mistake. Maybe we should have allowed really huge objects to be sent as a single chunk. But we're running basically 1985 kind of ideas. They're far from perfect, and it happens that 1,000, 1,500 characters is about as big as our chunks can get. So if you look at the paper book, The Inevitable, War and Peace, which is, hundreds of pages long, the phone book, we agreed to ship all that stuff over the internet. It's just going to get cut into chunks, and that's part of the solution, and the solution has created its own problem. So back to all of our layers stuff. We're not going to get into layer 1. Layer 2 is the final module. Layer 3 is the second to last module. Layer 4 is today. Layer 4 is module 2. And it's this conversation that takes place between the two end stations or endpoints that has the context and the capability to make everything right. By the context is, let's say back to our book example, we have 3 copies of page 100 and we're missing page 105. That's the sort of problem that the end stations have to work out. Okay? So in the theory kind of space, we're not moving our Bonaventure textbook pages very far. We're maybe up to page 73. And I will kind of misquote kind of a football quote and from my outline on page 1 of slide 1 of 6 today. When you forward messages across a network, such as the internet. 5 things can happen, and 4 of them are bad. Obviously, the good one is if things go through correctly the first time in order, no duplicates, no gaps, no delays. And the reality is things will be duplicated or lost or delayed, which means they show up out of order. And that's the problem that the software has to fix. And it happens when we are talking about software that resides on your personal device, laptop, computer, phone, tablet. It's huge. There's a lot of capability to put large, complicated bodies of software on those kinds of devices. Much less so than those things that sit in the closet. So we're going to introduce the transport control protocol, the transmission control protocol at the transport layer in kind of 2 perspectives. One of them is the network's perfect, but the endpoints are not. And then the network's imperfect. And maybe that will make a little more sense. To add the notions of the of feedback, control plane, and how we number our parts. So on to slide numbers 2 and 3. In fact, you wouldn't hurt to look at slide number 3 really quickly with that kind of fish diagram. The fish diagram actually has official standing in the Internet League. I kind of sort of think it was invented by my friend Paul, who until recently was the director of the Ohio Academic Research Network, who was part of a global initiative to set standards for Internet technology, and a nice guy. And so the fish diagram, I think, is part of our discussion because this was how he and his colleagues built the Internet. So back to slide number 2, the context is messages passing from one, I will say, host to host, or endpoint to endpoint, or station to station through a network of routers over some wide area network infrastructure per the fish diagram. So I have 6 nodes in the fish diagram, and each node consists of a device that I will define as a router, and the router determines which is the best path to reach the destination. I'm also saying that the proper geographic context for the fish diagram on slide 3 is wide area network, which is intercity. I guess it could be Cleveland, Columbus, Cincinnati, Dayton, Toledo, Akron, Canton, Youngstown. That's far enough apart, but it's not building next to building on campus. It's probably not this building, that building in a metropolitan area. Might solve that one a little differently. We have a lot of different options, but this is clearly what you do when you have branches of your organization spread out over a wide area like a state or nation or the world. So the usable payload now, the contents inside the envelope is usually small, on the range 500 to 1500 characters, a character meaning like a typed character, typed letter, or numeral typed. The messages are fragmented and then reassembled. It happens that if the message is too big to fit through the wide area network link to the next site, it will get cut into smaller parts, and they are just passed through the network as smaller parts, all headed toward their destination, the destination of which is tasked with reassembling all of the messages and fragmented messages back into the whole. It is only at that point where the message is presented to the application layer, and then thus the user. Segments are the protocol data unit for layer 4. These segments can be damaged, have errors in them, because errors are certain. There's an error rate when sending stuff over radio or wires or glass. Could be 1 in a million, could be 1 in a billion, but errors happen. Segments can be lost. I don't know where they go. They can be delivered out of order. It happens that if you look at the fish diagram, if something happens along the fish diagram, then packets might follow a different route to the destination. Doesn't matter exactly what they are, but let's just assume one route is quicker than the others. And so we must accommodate the fact that these things can be delivered out of order. And because our solution to a lot of stuff is just have stuff to have parts retransmitted, it is completely possible to have two copies of the same thing in the ingress of the end station or end host waiting to get put back together. There's a lot of reasoning, a lot of logic that goes along with those 5 anomalies, and there's a lot of rules and a lot of statements in the algorithm that goes to put this back together again. And that's why it takes a real computer or a real smartphone or something along those lines. We can't do this with a simple device. We can't put these things back together again in a simple device. We defer that to the endpoints. So, because there's a lot of work to be done here, it's going to be part of the operating system in the computer. And so, we're hinting at this point without really explaining how do we detect an error so it can be, something can be declared an error and asked to be retransmitted. I'm describing that as a problem. I haven't exactly solved that for you yet. That's coming up, not today, but that's coming up on a subsequent lecture. So with that, we go from messages to everything that could go wrong does go wrong as a matter of culture, and we just do it over again. And that obviously there's a lot of pieces, parts to get put back together again by the computer at the far end. And I consider your phone to be a computer by any standard. Looking at advancing to slide 3, the thing on the left-hand side is the fish. The thing on the right is the cloud. If we don't want to deal with details, we just hide them behind an opaque structure such as the cloud, and we're done with it. And that is honest. That's not evasive or elusive. That is accurate. And stuff not only on the inside of the cloud can have its details obscured or abstracted, they could also change, and we would have less to worry about. On to slide number 4. So case one is sending things over a perfect network. Over a perfect network, and case 2 will be over an imperfect network. So here's a couple rules for sending things across a network like a fish diagram that the component messages that must be reassembled to recreate the whole object arrive in what I'm calling an ingress buffer at the receive station, kind of a staging area, kind of a loading dock of sorts, that it has fixed capacity, and it's where the work is done to see if to reorder, to resequence, to deduplicate, and to identify the gaps where something's missing. And it takes up space, and it's possible for that space to be to overflow if there's not enough room set up for that. Not a trivial point right there, because the speed of the networks these days is just increasing by factors of 10, by orders of magnitude, it seems like annually. And so when the data rate, we have data rates in the Google world over 10 terabits per second. Our campus is typically 10 gigabits per second, on its way to 100 and 400 gigabits per second. So the loading docks have to be pretty good. They have to be pretty substantial, and those exist in chip memory. As a practical note, sometimes people say, why is my computer not fast enough? And it's actually the lack of this ingress loading dock space. It actually is, in theory and in practice, adding more RAM memory to the computer not only avoids the overflows, it's the best way for users to improve the, everything is based on user perceptions. Perception will increase the most by adding RAM. Do we need faster processors? No, generally not. Do we need more cores and more processors? No, probably not. Do we need a faster network connection? Generally not. Having more RAM in the computer is historically been proven to be the best way to improve one's perception of performance. And if you're on a wireless access link, we've got some other things to discuss as well. It may be that the receiver, if it is full, it can call timeout and it can tell the sender to stop. This is a scenario of moving things from the loading dock into the general store, into the compute part. The clearing of the loading dock does have a mode where the receiver can signal the sender to back off. And it happens that because every message, as I mentioned in Module 1, must be acknowledgement, that the receiver will constantly be acknowledging its ability to receive more and to negatively acknowledge anything that's been that has arrived with errors detected in it. This whole business about feedback can be more specific or nuanced all across networking, and I will generalize this as kind of an idea of control. This is a dialogue between sender and receiver, and each, in addition to the content of what's being sent, can transmit kind of instructional information as well. Sometimes we do that in the same channel where we're doing the data itself. Sometimes we actually have a separate channel where we can go do that. That is the future of networking. Future of networking is, if there's a lot of excess capacity, is to coordinate better between sender and receiver in the network itself. Getting ahead of myself just a little bit, but you got it. Case number 2 is, when the network itself is something less than perfect. Case number 1 is everything is transmitting well and receiving well, just a matter of the disparity in rates between the sender and the receiver, and the possibility of signaling going on between the sender and receiver to slow down or to pause because the loading dock, in a store or a factory or something, is not the ultimate destination. Okay, slides number 5 and 6. What if the network itself is something less than perfect, meaning the probability of an error being introduced across the link is real? We're not a signals class. We're not a signals major. Before we're finally done, after you will have mastered all the really important stuff, we'll share some of this, electronics, physics kind of stuff. But it's like, you don't need to be an engineer to do this. In fact, if you are an engineer, you may be disadvantaged because your focus is on details. The user's perception of performance is based on end-to-end issues, which is why we're beginning at the application layer. It's true that when we look at the binary values, remember back to the binary stuff in the assignment for number 1, zeros turn into ones, ones turn into zeros. That's how errors manifest themselves. Call that flipping a bit. So there's a bit that's wrong, and that it just happens. And so it happens. This is really interesting stuff. And pay attention. I guess this is the third bullet on this. We will grant ourselves an additional field to accompany each transmission that has certain mathematical capabilities that allows us to detect errors. Think of it as a shipping list. Everybody does e-commerce, so you buy something online, and there's the it. Okay, and then there's a piece of paper that's also in the box that should describe the stuff that's in the box. And so theoretically, you could compare what you've received in the box with the list that's on the box. Now, we're all very savvy personal consumers, and so we know what we ordered, and we know what we bought, and we know what's in the box. But in a more commercial, industrial kind of setting where we have engineers and purchasing agents and people working the loading dock and receiving things, it's like they might be obtaining, thousands of different items per day, and they may not even know what these things are. And so it's essential for them to match the items received, the items and the quantity of those items with the list that accompanies them. And so that in and of itself hopefully makes kind of perfect sense. So let's do a little math here. We're not going to do it. We're going to talk about math, which is probably better than doing it anyway. If I perform, if you look at the ASCII hexadecimal binary representation of stuff, if you recall that I can count to 16 by ones in binary, honestly, I can count to a quintillion by ones in binary. But that's not important. The important takeaway from that very witty prior statement was that you may say, I'm sending the string 411 Woody Hayes Drive, which, by the way, is Ohio Stadium. It's also, it's a descriptive string, 411 Woody Hayes Drive. It's also a gigantic mathematical number. It's a gigantic mathematical number. So it's how it is interpreted semantically by the receiver, what you do with that data. So it's because it's simply at one level a great big number, I can perform a function on that number and get a result. If I perform a function on that great big gigantic number and get a result, and the result is a rather small result, and I just tack it on to the end of the message, and the receiver at the far end, far away, performs the same mathematical function on the payload that was sent, it can then compare the answer it got to the answer that it was shipped. And through the certain mathematical powers of the equation that was performed, can detect errors in the transmission and receipt of the payload. Let me say that again, because if we were doing Nobel Prizes and this stuff, I think it is just absolutely total genius work. It's referred to as a cyclic redundancy check, yet another meaningless name, but the CRC, also kind of street called a checksum. Every message that is sent is whatever it's supposed to be, but it's also a really big number. Perform a function on the really big number and send the result along, a really short form of the result. And the far end will perform the same function on the same payload, and if it doesn't get the same result mathematically, then it's an error and it will beg for retransmission. If it gets the same answer as the sender got, then either the system's really flawed or it came through correctly. And we do that. We do that on everything that we send from one node to the next, and from end to end. Pretty genius stuff. It's okay if you want to play it back. I know I don't sound any better on the replay, but listen to it. If no error was detected, then, have a nice day. If they do not match, knack it, force a retry. So doing errors is pretty genius work. It's elegant, it's mathematical, it's all the right things. Reporting on data that something that didn't show up is actually a lot harder. Try to track a missing package, an entirely missing package. It's a different process than an error that got messed up. An error that's lost, may or may not exist someplace. It might have never been shipped, went to the wrong address. It matters if you're getting billed for it. And so there's a value associated with the transaction. But on slide 6, we'll call this the case of the missing segment. So, on the prior slide, the receiver didn't know what it was going to get, but it had some means to check the accuracy of what was sent. In this case, nothing happened. Okay, and that's a much harder scenario to work with. So how long shall one wait before escalating and complaining that the order has not been received? If you complain too quickly, then you've wasted everybody's time. And if you wait too long, well, you're without the goods. So it happens that the receiver is innocent. the sender has the responsibility to make sure it gets through. In this case, starts a stopwatch, starts a timer as the transmitted message departs. It happens that, these things don't have eyes. They don't know geography. They don't have any sense of expectation. But if the two endpoints have been communicating for a while, we know how long a round trip should take. It's part of the genius of this thing. It's anywhere, any size, any place, any device. And so we're not going to have a different version for going to Europe and a different version for going to Toledo. We're going to have the same version of the code, but as there's a dialogue between the two endpoints, there's kind of a sense of how long a round trip should take. And the right answer is we'll wait 2 units of the round trip time before declaring something lost, we meaning the sender. Sender starts the clock, knows how long it should take, waits one of those, waits a second one of those, declares it lost, and retransmits it. So it happens that there's a lot baked into the notion of the round trip time. Round trip time can fluctuate over the course of the day. Probably in some cases at 3 in the morning it's really quick. Some cases, this morning I had my laptop working from home, and then later I was on my laptop at the branch, and now I'm at a library. And so the same TCP using for me to upload my audio files to Blackboard has to retune itself based on the elapsed time it takes to get from here to the Blackboard server. I have medium to poor service at home, so the round trip times are low. When I go to the branch campus at OU Lancaster, it's really fast. And actually, I don't know what it's going to be for here at the library here in Westerville. Probably pretty good as well. So the case of the missing segment, the reporting on missing stuff is hard because, you don't have a lot of evidence to work on. Dealing with the imperfect network and the perfect network are very interesting cases. And intellectually, isn't it nice to work with the big picture? Isn't it nice to be able to work from a problem statement and intellectualize a solution? This is what networking is all about. Nobody remembers who the professor was. I'm not even sure we could find out. But the founders of this were thoughtful students who were in student mode. I think for a lot of them it meant they were really young, but in all cases they were just really ambitious and had a great team and probably money to go work on these projects. And literally they just went from one problem to the next. They found out that they typed LO, the LO part of the word login, and it broke. So then they had to go back to the drawing board and think about why, and then think about how to fix it. And we've generally been constrained with what our computers can do. And so it's where can we put this code to fix this problem that's best? And it happens that it ended up going to Windows and Mac OS was the best place to go and do it. A little bit long today. I appreciate your patience and endurance. Welcome now to Unit 3 of Module 2. We are continuing on the mystery of Layer 4 in the end-to-end connection-oriented coordination in order to achieve the error-free, timely delivery of messages of any size between any kinds of devices anywhere. Okay, so I want to really add one general comment before we dig into the 6 slides for today. In the technical engineering kind of software development world, it seems like most of the effort, most of the attention, most of the emphasis goes on obscure cases that may rarely, if ever, occur, but we have to be prepared for it. Again, it's not because we're paranoid or depressed or anything like that. It's simply that, and there's a name for this, it's a moral hazard argument, that if this situation might come up, you need to have a solution for it ready. So what it means is our allocation of resources on the development side is tilted toward anomalies. And I think that really can divert our attention away from really the big picture, which is we can send over the internet anything of any size to any device at any time, and it works. And the nature of the duality idea is that it just simply works. The harsh reality is it gets cut up into chunks, and the chunks ultimately have to deal with the reality of the topology of the network and the presence of errors. And so we really have things like duplication and loss and delay, and they have to be solved, and they have to be hidden from the user. And so from a business point of view, if you're not dealing with infrastructure, these ideas are almost always transparent, except for one thing, which we'll bring up in slide number 4 today, which will become probably the only math that we do in the class, and it will be the basis for our assignment for this today. I did manage to leave out one idea on the prior slide decks to date. When we cut messages up into more messages, they get numbered. Integer numbers. It would be really great if they started with like 1 or 0 and counted up ascending from there so we could keep track of our parts. No, they just take some number off some other clock source, number source, and start counting from there. And so the notion of a sequence number is it's a great big number between 0 and 2 to the 32nd minus 1. Do not ask. And we use that as the beginning in our business of leaving no character behind. 6 slides today. Going to restate our problem a little bit more, perhaps using a little bit more vocabulary that's less descriptive and more technically accurate. Add really just one more concept, but it's a good concept, or I wouldn't be teaching it to you. Okay, slide number 2. I struggled to find an elegant way to describe connection-oriented and connectionless. And we haven't done it yet, but the relationship between the two endpoints through this cloud of unknown networks is the basis for what's called the end-to-end problem. The end-to-end problem, I think, is best understood from the outside in, from the top down, and that what is it supposed to do? And are we done that? Are we done yet? Are we there yet? So we're a top-down approach. Our initial model was really apps over the infrastructure, that the peer applications, the peer levels in this layered model communicate with each other. The canonical, kind of the official 5-layer model that you have to memorize, and this end-to-end problem where the show must go on. We must have error-free, any size delivery from the infrastructure up to the application, and things go wrong. I have now on the 5th bullet point on this slide going to use some new words for us, some new ideas that the layer 4, which is done in the operating system of our devices, which is hugely important to us, is end-to-end. It is full duplex, in which, unlike humans, the two end stations can be communicating to each other at the same time. It's reliable in that everything that's supposed to go goes, 100% accurate, delivered end-to-end. It is connection-oriented, and I will define connections in unit number 4. And it is oriented toward bytes. A byte is a character. A byte is one letter on the ASCII chart. And so you in Module 1 mastered the art of translating things using the Jim Price ASCII chart. Those are just letters. And the official definition, out of the book is the end-to-end full duplex reliable connection-oriented byte service. All 5. And because it's 5, it's like a wonderful test question, and I can grade it without looking at the answer key. By the way, I grade all this stuff myself. Slide number 3, just a quick review. Slightly different verbiage to take it a little closer to kind of tech speak. We had really 2 cases, the one where the network is perfect and one where the network is imperfect. So for the perfect network, we have the loading dock problem where the ingress activity that contains the errors and the dupes and the gaps has to sit someplace. This is where, regardless of what the question is, the answer is put more RAM. If you have a high capacity channel attached to your device or site, we can run out of room. There's a little bit of a control channel in place, a little bit of a control plane where, there's ACKs and NACKs, there's timeouts, there's messaging that controls that dialogue. Main bullet number 2 on slide 3 here is that bits get flipped, and we have a mathematical way of doing error detection based on the CRC, and error correction, which is like just have it sent over again. It's really not worth such a grandiose name, but error detection leads to error correction, and then the lost message problem is, think about it, kind of justify that to yourself. How do you fix the message that you didn't get? It's the responsibility of the sender who must wait 2 round-trip times, and the round-trip time is constantly being adjusted situationally. Slide number 4. Actually, that's kind of a dumb title, but it's the title of an article that I'm not sure if I read it or I wrote it, but latency means the delay, and really that's what users detect. So in a consumer-facing world or a business enterprise kind of world, people don't call to say things are going well. People pick up the phone and say, why is the network slow? People don't call and compliment us that the trucks are clean, that that we're doing all these other sorts of things. This is a complaint-driven kind of enterprise, and it doesn't matter what it is. The symptom is latency. And honestly, not to be trite, but there's modest delay, there's increasing delay, and there's this like infinite delay. And infinite delay comes from something being broken. And is you can go back to the fish diagram. We generally have a couple ways to get from here to there. And so, latency is how customers measure the entire health of the network. And I firmly believe that customers' perception is our reality. And so the performance measure that emerges from networks in operation, well, they are things like latency and security and cost, but latency is really it. And so in our case, latency is measured, because it's time, latency is time, it's measured in like milliseconds. And milliseconds is the number people should care about, which of course means it's the number that's never advertised. The number advertised is the data rate, which is like bits per second or megabits or gigabit per second. And I think that's a little bit of misdirection. Thank you, marketing, advertising community. It's actually easier to deliver chips and boxes and stuff that have a sticker on them that says we operate at 1 gigabit per second or more. But, let's not be fooled by that. I believe that latency is the number that we should care about. And I bring this up at layer 4 because layer 4 is how well our applications perform. If I started my stopwatch, if I'm going to download a movie, not stream a movie. I'm going to download a movie, and I know how big the movie is. Let's say it's 2.7 gigabytes, I believe, is what a DVD might look at. I start my stopwatch. I start my timer when the download begins. So I have the size of my object. And you can go to like the File Explorer, and you can always see what the size of the object is. And then you get the elapsed time. So, if I've got the object size divided by the time, I get the real effective data rate. If I take my object size and divide it by the data rate, I get the time it should take for something to be delivered. Now, to be quite honest, let's interpret this just a little bit. Most of the time, if I'm clicking like on a link, the link is like, make up a number, 80 bytes, 80 characters. 80 is a small number when you divide it into something large like a data rate. Our data rates begin at 1 megabit per second. LTE is running like at 100 megabits per second. Our in-building networks are 100 to a gigabit, a billion bits per second. There are 8 characters in a bit, so one must be careful with that. You'll see that in the example and the exercise that I give to you. But actually, there's the data rate you're paying for, which is a number that's on the contract. And then there's the data rate you actually get, which you can figure out by dividing how big the thing was by how long it took to get. And, this does take us into scientific notation, and or we do it in Excel. Single symptom, vocabulary word, possible test question. The single symptom of anything that goes wrong in networking is delay, or the perception of delay, fast, slow, something like that. And it's really hard to differentiate between really slow and broken because our patience kind of runs out at the really slow part. We hit that reload thing, which makes things worse. But sometimes things are actually broken, but I think for the most part, we're dealing with the really slow, and we should not accept that. It happens that for me, I tend to want to prefer to operate wired than wireless, because the wireless performance is based on those other wireless people around me, and so I would like not to have to deal with that. So if every message has to be acknowledged, then I've got a scenario here where I'm going to send and wait, called stop and wait. So in the upper picture to the right that I've labeled SWP, send, wait, send, wait, send, wait. If my messages are relatively small and my delay is related perhaps mostly to the distance between the sites, then I could be spending the majority of my time waiting. I could, in fact, be spending the majority of my time waiting. So it happens that I might prefer actually to send a bunch of things and get a single acknowledgement for a plural quantity that I will refer to as a bulk acknowledgement. If I have a bulk acknowledgement, if I choose an environment that I described as bulk acknowledgement, then I got to watch those numbers. If I'm sending 4 at a time, I'll send 1, 2, 3, 4. Expect an acknowledgement, probably ending with 4, and then go ahead and send 5, 6, 7, 8. It happens that I teach it this way and I show it this way because it's really not a bad sketch. Which means the last idea on slide number 4 is these things can talk and listen at the same time. So we want to not stop and wait. We want to do a bulk acknowledgement where I have a window, not Microsoft Windows, but I have a window, I have a gross or a bulk of these things I'm going to send at once and get an acknowledgement back. And I can be sending and getting acknowledgments at the same time. Unfortunately, I can't draw that. I don't have a picture for that. It doesn't do well in black and white and on two-dimensional paper. But, SWP, stop and wait. Number 2 on slide number 4 is called the sliding window flow control. And then and that's where we'll just stop. That's the end that's the end of what we're going to do, but I include number 3, which is the sliding window flow control with full duplex. But that's like one step too far, and I regret doing that already, but it was in the slides. Okay, 2 more and then we're done with this. Slide number 5, in our particular case, we've had error detection, which is based on CRC, and then we have error correction. And error correction is brute force, which means the far endpoint will provide a negative acknowledgement with the number of the frame that was broken. So in my sliding window flow control thing, and I'm not sure that the sketch on slide number 5 is particularly clear, but the frame that was damaged is identified by its sequence number. The negative acknowledgement contains the sequence number. And so there's a couple responses to that. One of the responses, and just listen without looking at the slide, one is to go back, request the sender to resend the damaged one and everything that followed it. It's actually pretty easy to do. If I'm sending 4 and number 2 was damaged, negative acknowledgement on frame 2, it then has frames 2, 3, and 4 resent. Logically, it's a little easier to implement. It's if better is the enemy of good enough. While that other thing was called go back in, the selective repeat request, the negative acknowledgement triggers the resend only of the errored frame and not the good frames that followed it. And so, I don't know. Again, this was developed by students, and so, they did stop and wait and found out that their 10 megabit per second chips were running at maybe like 30% of the line speed, which is welcome to my world, which is what happens. And then somebody said, well, let's send a bunch of these at once, call it a window, and then go back and retransmit everything that was bad. And somebody said, well, let's retransmit only the thing that was called out as bad and move on. So I don't know. It's a function of the window size, and the window size stuff is kind of beyond the scope of what we're going to do in this class. And so what I will say on slide number 6, I'm very interested in the concepts and the diagrams, but not the labeling scheme, because I borrowed this from Professor Bonaventure, which is non-standard and overly complicated, and we want to stay focused, all right? We should know how to compare SWP in sliding window flow control, SWP, SWFC, GBN, and SRP. And reflect upon this, ponder this final slide in that, which of these is most efficient? Actually, how do you measure efficiency? Efficiency is kind of like work done per time unit, work done for a unit of time. So if my time is, 10 milliseconds, how much did I actually send in that 10 milliseconds versus how much did I sit there waiting to get a reply from the other end? It's always what's in the denominator. So in this case, this is the most elegant, most interesting part of the class. It happens that the principle of the transport layer, we didn't even know we needed it. We didn't even start working on it until the errors started showing up because stuff was getting lost and duplicated and damaged and all that. And so let's put TCP on our computers and let's just start adding features to it every time we think we have a good idea. And so, next thing you know, we end up with full duplex, selective repeat request, automatic repeat requests, and it's what we might refer to as feature creep, but it's for a good cause because consumers and users want the best performance, and the best performance is simply, how fast can we get this stuff done? It's not a subtle answer. It's not a subtle answer. It's a pretty good picture, and we're not done with the good pictures. We got a couple more good pictures left to go on this stuff. I'm trying to keep the pictures consistent with the text in the book, and I hope that helps. So we are at the halfway point of unit of Module 3. I think we'll do a little problem on transmission delays, and see you soon. Welcome to ITS 2010 Module 2, Unit number 4. And someday maybe I'll just load up a bunch of the takes that I have to cut after about 30 seconds into this. You are actually hearing the better versions after I've messed up more than a handful of times. In 9, now 10 short lectures, we have really hit some amazing ideas. And I'm not going to say they're secret ideas because we don't conceal them, but these are ideas that intuitively people might not have come up with on their own. And my word for that has been duality. It kind of sort of looks like it's working one way, but deep down it's doing something really completely different. It's all about the software. It's not about the hardware. We've accepted the challenge of objects of any size to be transferred. We made that promise probably in the days of floppy disks, magnetic removable media, and now we have to keep that promise in the era of people moving 8K DVDs, images across the internet for movies of any length, and so it works. Perhaps the largest idea to reflect upon is that we divide things into chunks. We send the chunks because there may be errors as we send things, but the errors are in a singular place, and for the most part, our chunks are going to be unaffected by errors, and the chunks that do have errors in them simply get resent. That's pretty easily explained. I did that in one breath. The other part, perhaps, is non-intuitive whatsoever. The internet, I have not mentioned, is basically owned by, I don't know, a lot of different parties between any two particular locations. I'm thinking about Northern California right now, rather than recording here in Ohio. The phone company there, I believe, in LA, it probably is Frontier now. It had been GTE. Northern California, let's say it's Verizon. And the ownership of the media and the equipment changes as we cross the country. To switch into the train metaphor, if the desired load is sitting in a boxcar or a rail car, the tracks that we'll ride over from New York to Seattle or something like that, a lot of different organizations own the tracks that the train cars go over, and that is absolutely exactly true for us. That we kind of conceal that under a single brand. The brand may be Spectrum or Everstream or AT&T or Verizon, but the actual ownership of the underlying stuff is so complicated that we just draw the picture of the cloud over it. And because coordinating cannot turn into a relay race every time we go over a network that somebody else owns, we don't have people or time or dollars to coordinate that. We delegate the coordination of the integrity of delivery to the receiving end, the sending end and the receiving end, what I call the endpoints, whoever, wherever, whatever they may be. I mean, I'm looking at a computer and I'm going to be posting this to Blackboard, which is another computer server sitting at the Blackboard Corporation in Ashburn, Virginia, momentarily. And so the integrity of, in particular, this MP3 file is a negotiation between my computer that'll do the sending and their computer which will do the receiving. And all the stuff in the middle, I'm not an uncaring person, but I don't really care. The egress is my AT&T Uverse from where I reside, and then from Uverse, and then I'll go on a bunch of different networks. Don't need to know that in order to get my work done today. And we're 4 minutes in. We are not advancing many pages in the book. The book is there to support what I do, to provide a reference for what you do. Obviously, the whole internet, is a reference of varying quality. But I always want you to have something to read if I'm not doing it all that well by myself. Theme today, the many steps of reliable end-to-end transport. And so let's kind of look at what we have here on slide number 1 of 6 today. We've taken this inherently unreliable, error-prone medium that we call a network, and we've created a reliable scheme that I will call transport, that I will call TCP, that makes it appear to perform well. Doesn't seem to generate a lot of complaints by users to the providers and the people like me who have to keep all this stuff running. So we did that. We've accomplished reliable end-to-end transfer of information it is similarly invisible, but in addition to the actual tracks, the path that carries the data, there is a virtual or functional control plane that coordinates things between the sender and the receiver. The future of networking is software-based control planes, and the future is wireless, just to throw that in there. So this business of the control plane is there's a separate channel. You have you don't want to imagine somebody holding a phone to the left ear and a separate phone to the right ear. You don't want to do that. I don't want to do that. It's not a pretty sight. But the phone on the left ear is carrying on or is part of the content delivery of some very important information, and then the other phone on the other ear is just to make sure that the conversation is working out well on the other side. Poor metaphors. You can always count on them from your instructor here. We've created an entire apparatus for error correction using the checksum or cyclic redundancy check and error detection. The error detection is done via CRC. The error correction is done by requesting retries. And then finally, we've added an elegant measure using bulk acknowledgments to spend as much time sending data and the least amount of time waiting. Sliding window flow control with the go back in or selective repeat request. It's a very interesting drawing. It is the culmination of a lot of work or a lot of thoughtful, hardworking people. But I believe the picture shows 4 messages being sent per acknowledgement. And theoretically, that's 4 units out of 5 of time, 80% utilization. Might compare that to the stop and wait model, which had like send, wait, which I depict in my chalkboard kind of class as 50% utilization. Well, 80 is better than 50. I'll stop with that. And today we're going to add this notion of what I will call state or condition, which describes this relationship between these 2 devices that are far, far away that are doing real work, that are separated by whatever network apparatus is between here and there, and we don't care about them. You have my permission to say you don't care about that, and we will use the icon of the cloud to cover up all the stuff in the middle that we don't care about that might be changing as we speak. On to slide number 2. This is a really big deal to me, and because it is, for me, I'm sharing that with you. State or status or condition is an important word in a lot of systems. There are a lot of things that are truly stateless. They have no memory of what happened before. They have no predictive powers for what's going to happen next, and a lot of devices in particular are stateless. And a lot of systems are stateless, but there's also a lot of things that depend on what happened before. Mathematically, you can't do that in an equation. When you do an equation, when you solve an equation, rate times time equals distance, it is rate is equal to the product of distance is rate times time, whatever I said. But, we don't have a mathematical scheme that's nice, that allows to say, well, the solution for the next part depends on a bunch of stuff, and the solution to the prior part at t equals t minus 1. So in our case, we are in that mode of thinking where we have indeed a logical connection that connects the near computer and the far computer. I've described it as virtual, ephemeral, or notional, if those words make you feel any better. But you do know when it's connected, and you do when it's not connected. And so ultimately, it has 3 very technical phases. You'll want to make a note of this. These are important technical phases. Their names are like beginning, middle, end. I'm being facetious. So there's a startup or a setup phase, which can get messy. There's an operational phase, which is actually very simple. It's very peaceful. And then there's a teardown phase. So set up, operate, tear down, or beginning, middle, end. And in the drawing I get to in slide number 4, it's top, middle, bottom. But it tells a story. I mean, you can't begin unless you're set up. You can't operate unless you're set up. And then once you're done running, well, you have many different variations of normal and abnormal termination to the connection. And when it isn't there, it isn't there. And the first thing really important applications do is they form this virtual, ephemeral, logical or notional connection to the computer at the far end. This is the ultimate role of the control plane. The ultimate role of the control plane may or may not be a separate set of wires, but it is the act of coordinating and knowing which of the many states the system is in at that particular time. Yeah, we kind of mostly do it in using the same physical channel as the internet, which makes things even more awkward, but we don't want to talk about that today. We're going to defer that. That also exists as a set of commands and responses, and in the command response dialogue in our protocol, in our very organized protocol scheme, allows us at any given time, get this, to know what state our system is in. It could be off, it could be doing setup, it could be really operating, and then it can go to some sort of tear down or disconnect phase, and then it can fall asleep. And those are good states. So setup, transfer, or some synonym, and tear down are the official words for this on the slide number 3. And I can't leave it alone. I can't leave this alone because when we first defined the transmission control protocol, I permitted these devices. I imbued these devices with the ability to send and receive, to talk and listen at the same time. And I'm going to pay for that. I also allowed these systems to work at arbitrary distance. That's how the mathematician would say it. Any distance, and you can specify the distance at runtime. I, again, will be transferring my MP3 files today, some 350, 400 miles to the, geographic miles. I don't know what my route miles will be, probably a little bit extra to this. So to slide number 3. And I hope you appreciate the conversation. There's a lot of richness, I think, in our, it's a one-way dialogue, but I'll call it a dialogue. Every message must have an acknowledgement. That was a rule. That was like a rule for maybe like Module 1 someplace. The left-hand side, the device desiring the connection makes a request, expects an ACK. Some transfer takes place, could be sending, could be receiving. It's not important now. And then sends a request to disconnect. It's not polite just to hang up. Sometimes things will happen and a disconnect will take place and then it will reconnect automatically. So the basic case is, beginning, middle, end, setup, transfer, tear down. The advanced model is we're actually going to have a connection running in both directions because we imbue our devices with full duplexivity that they can send and receive at the same time. So while one station generates a connection request to its faraway partner, the faraway partner reciprocates by creating a second connection in the reverse direction. And we'll run them both at the same time simultaneously. Finally, the official formal bullet point that says we will number the parts. I wish we could number them starting with 1. We don't. We number them with whatever the next number is on the wall, kind of like going to the motor vehicles. It's like you pick up the next number and that's you, and you wait. We will use the sequence number, the range of sequence numbers, to make sure that every single one that was supposed to move got moved. We'll use that to identify duplicates and gaps, and if we have to request retries, we'll retry. We'll summon that by the part number. Either end can terminate the connection, and then I refer to that as the dreaded idle or walk-away mode. A lot of people just kind of walk away. That's not a good idea security-wise. Maybe Windows will lock the screen at some amount of time. But if you walk away with a tab open in a browser, then you're causing pain to the universe. That realistically, when you're done with whatever session was associated with what you were doing in that tab, you should close the tab and or close the browser. And if you aren't already set up that way, go under your options or settings on your browser to make sure it deletes all the evidence of everything every time the browser closes. Be vigilant for bad actors, malevolent actors. Should really, you know, there's an expression called session hijacking. We literally have to tidy up when we're done with this, and clearly I never even leave my office without doing a window L, which is to lock the screen on my Windows machine. Not that I don't necessarily distrust all these people with PhDs around me. It's just a habit. Who knows? I mean, never be coming back. On to slide number 4. Canon, I think, is a Latinish word for law. So this is the canonical state diagram for the layer 4 implementation known as the Transmission Control Protocol, or TCP. 3 words that don't mean a whole lot. But the TCP has a state diagram. It goes from top to bottom. Does not go from left to right, ever. This one goes from top to bottom. Do not ever even try to memorize this or think of memorizing this. I'm not even sure there's 11 or 14 boxes in this, and it's not important to me because the story it says is normally it's closed, then it opens, and then the box in the middle is so important, called established. Established is where information gets transferred, and then as you can see in the bottom with 7 different boxes, there's a lot of ways for these connections to end. And only one of them is good, and the others are just kind of accidental, but it happens. You would think that it would begin with a meaningful word like begin, or open, or connect, or set up, but they don't do that. They actually use the notion of synchronizing the sequence numbers. So if we're going to begin at the beginning, we don't get to begin with number 1. We begin with the next available number, whatever that is, and we request from near to far, and then from far to near, that we synchronize against the current sequence number. And they couldn't just stop and leave it alone after making so many mistakes. They, instead of calling it sync, they call it SYN, which is pronounced sin. So we'll talk about SYN requests, which sounds stupid to hear that. So we have the pairs of SYN and FIN. And so the SYN command from near to far is to establish the connection based on the current sequence number, and here it is. And then the normal approach is to, I have 2 more slides to get through for this. So I'm going to pause. This is a big deal. You don't memorize this. You memorize the thing that it's begin, middle, end. The begin has to happen the right way. The middle, which is, again, in this kind of 80-20 rule, it's like, this is the part we really care about, so we don't pay any attention to it. The actual transfer part works pretty nicely. I'll embellish that, in a subsequent unit, but it works pretty well. And then the fin part, can be normal or abnormal, can be started by either end, so we end up with a lot of different options, intentional or just timeout. So beginning, middle, end, and the end can be messy, just like all relationships. On to slide number 5. So I've got this thing called the 3-way handshake. I don't really want to do it. I could skip it, but it's such an odd thing to think of 3 people shaking hands at once. It's not even a decent metaphor. But what happens is that distance matters. If there's any kind of true lesson of going from classroom networking to networking in the wild, is that distance makes everything more complicated. It's one thing to connect from building A to building B on campus, and then because we control all the variables in that. Well, maybe we're going to connect into building C, which is in another city. Then all of a sudden, there's a lot of different parties and parts and products involved, and maybe a third-party company like Wired, AT&T, Verizon Level 3, could be a cable TV company. It just gets complicated. It's so much simpler just doing it in the classroom. The 3-way handshake thing permits us to go any distance at all. And so it happens that in the same way that it takes a football on a punt or a kickoff a little bit of time before it lands, Might be, a couple seconds before it lands. Well, we're operating at the speed of light, so it's not taking us a couple seconds to get from here to there, but it might take us a couple milliseconds to go from here to there. And, the way a lot of this stuff works is that you start doing this over and over again, the links of the chain to get from here to there. Those milliseconds add up, and at a certain point, the millisecond is a thousandth of a second, they accumulate to the point that they can be problematic. And so to do a full duplex connection bidirectionally means going from here to far with an acknowledgement. That's there and back. And let's say there and back is 20 milliseconds. Okay? And then simultaneously, the far end, by law, wants to create a connection back to the near end in order to make it full duplex. So that would be like another, what did I say, another 20 milliseconds? So take whatever time it was and double it, because I'm going near to far and then far to near, each with an acknowledgement. So I have 4 network traversals, and I can turn those 4 network traversals, those 4 network crossings, to 3 by putting the acknowledgement and the SYN frame from the far end onto a single message, which is why if I look at my diagram to the right, and these are subscripted with the sequence numbers, and thankfully Mr. Bonaventure's art department started at 1 on this one. So we go from left to right, SYN, ACK, and then the reply should have just been like ACK. But they didn't just do ACK. They said, well, as long as you're sending an ACK, let me send a SYN along with the ACK. It'll get there at the same time. And then finally, we have the reply of the acknowledgement. So it's kind of ingenious, because network traversals over long distances are always longer and always take longer than mathematically we predict that they should. To cross the U.S. should be on the order of 10 milliseconds. It's generally 2 to 4 times that much to go from like New York to Cali. So please hold the visual metaphor on the 3-way handshake. The full duplex ACK would have 4 network traversals, which would be lengthy and might get noticed by impatient users. And then some wise programmer suggested overloading the first ACK with the second open, or SYN, or sync, or connect, or setup, eliminating 1 network traversal. Go from 4 to 3. And the book figure makes this simple idea hard. Thank you, art department. And concluding today with slide number 6. Either end can request the close. This is like real life. Either party, can request that the connection be terminated, or you can simply walk away. I should just quit. Well, I am certainly personally behind today. The system will time out or expire, or either end can initiate and the other end will follow. So the instructor's note, respect to the 3-way handshake, the normal case is intuitive or even easy. There are several abnormal, unlikely, or exception cases which must be considered, and program engineers overemphasize the exception cases, which is how we stay employed, which can obscure the normal case and its intent. Is that not the entire motto of engineering? It's not. I'll do that in a later lecture. Thank you for listening so intently. Thank you for caring about this class, and I hope you're learning. ITS 2010 Module 2, Unit 5. This is not take 1. Okay. So let's pause just really for a moment. Nobody knows about this stuff, but the things we just covered in the prior lecture in unit number 4 on TCP probably represents the greatest amount of software, the greatest number of lines of code, the greatest amount of effort intellectually of anything in the entire internet. Well, other than maybe what Unit 6 is going to cover, which is an embellishment. When I started developing software, we put it into chips and we try to cut down on the number of lines of the programs that we put into the chips because the chips didn't have a lot of room. And so I'll have to say this, we were really good. Fast forward to 2019, 2020, the code that runs the stuff we're talking about in Module 2 sits in the computer, in the server, in your phone. You know how much RAM, how much money you paid for the extra RAM and storage in your phone, how much disk storage that you put on your computer, a large number. And because the capacity was large and because the problem was small, the solutions are incredibly complex, and there's no constraint on how complex they can be. We could make them simple and say our sequence numbers start at 1. That would require some discipline. But no, we're going to allow our sequence numbers to be a 2 to the 32nd, whatever that is, a range that large, and create a bunch of complicated rules that go around that. We could have enforced, when we invented the internet, a true idea of a session where the user logs into the session and is going to be kicked off the system unless it gets completed in time, but nobody did that. So we ended up with creeping complexity, which is why the state diagram has more than 3 boxes in it. As we permitted it, we tolerated it, we indulged these programmers by giving them more RAM and disk and greater compute power. Look what they did with it. So we can backtrack just a little bit. We can coast on Unit 5 just a little bit. It's an interesting idea, and maybe there's a funny story to go with. I cannot be the judge of whether it's funny or not. A couple 3 pages in the Bonaventure book, if you're reading along. Actually, it is quite a bit of reading, but it's not all words. There's a lot of interesting pictures. I think the hardest part about the Bonaventure book is knowing which parts to skip. I regret to have to say that, but the hardest part about reading in general is actually, and this is proven, that being able to deal with the information you need that isn't there, which must come from your education and knowledge and your learning, by the way. And so it's hard for a thoughtful reader to read a bad book, difficult book, because you have expectations that may or may not be met by the book. And the only problem that's kind of in the same league as that is looking at this stuff and figuring out which parts that you don't need to know. And so enjoy reading the Bonaventure book. It's the real deal. It has both of those features in it. We'll talk about end-to-end. We'll talk about layers a little bit more today, and perhaps that will reinforce our understanding of this. And then we will move on to, we'll coast our way into Unit 6, slide number 2. Because we could, we put a lot of our programs on the device that's closest to us. Was a PC, then it was a laptop, then it's an iPad or a phone or what have you, where we're hopefully not keeping too much sensitive data on our personal device where it cannot be protected, where it might even be stolen. We try to put the high-value stuff on the server. One of my data centers that I visit actually has a physical moat around it. I did not see like alligators in the moat, but I will look next time. So we've got the distributed mode of client and server. We've allowed infinite or arbitrary sized objects, and we've said that we do not want to have separate versions for separate geographies. One version for close, one version for far away, that the system will just kind of understand distance as it is presented in latency and delay. Also, point number 3 on slide number 2, the application folks weren't compelled to actually understand what kind of network was running underneath it, other than it was running on a network. So the applications people, and this is one of the ideas I think we've held on to the longest. I actually met the guy who, David Clark at MIT, who is the, basically the inventor of the principles, the author of the principles, the application independent network, the network independent application. This right up there behind the layered protocol stuff. And that's one guy. And then he never did the work. The other people did all the work. He gets to sit under the Golden Dome at MIT every day. So it is clear that the application is in your hands. It is implicit that the server that holds the data for our app is someplace else, and it is a known, unknown, the place and the ownership of the interconnection equipment, links and nodes. We know we don't own it because we didn't pay for it. We don't even know where it goes or how it goes. We are going to know how it works. But the unclear who owns the network, interconnections, links and nodes. And then we simultaneously have a connectionless network and a connection-oriented relationship between the near station and the far station. It's a beautiful thing. Slide number 3. Well, I'll let you judge what you deem most significant. It's hard to go wrong with that. We have clearly a divide and conquer approach of the service model. My initial picture said it was applications over a generic block named infrastructure. And then the application layer never really changed, but I took the infrastructure box and cut it from one big box into 4 layers on top of each other. Well, the layer at the bottom is always the wires, which we'll call the physical layer. And then the layer right above that is the local area network part. Local in that basically it didn't leave the building. And then the third layer became the network. If the second layer was the links, then the third layer was the chain of links. And then when people found out the stuff didn't work right, they said, oh no, where can I possibly put the logic in that corrects this? Will it be in the wires? No. Will it be in the links of the chain? No. Will it actually be in the chain itself? No. Will it be in the application itself? No. And what's left? Nothing. So they had to invent a layer that went between the chain and the applications, between the network and the applications. And as John describes, the network folks who built the chain kind of left a trail. I'm not sure if that translates well into any other language, but the trail was lost, delayed, duplicated, or errored frames, and that problem had no solution until we invented it. The fix is this layer called layer 4, and we couldn't put it in the links or the chain because there simply wasn't room. And we couldn't put it in the application because we promised the application people they did not have to know about the network. But we still put it on their computer and we stuck it in the operating system. The fix, for R&D purposes, we did like a really lazy fix. And that is the topic for today's talk, which is the really lazy fix. Sits between the network layer and the application layer. And I call it, as in slide number 4, a shim. If I have 5 layers, I can't operate without a layer 4, but I can put a layer 4 that's really just a gap filler. And so I created a layer 4 that's a gap filler, and I gave it another undeserving name, this one being UDP, or User Datagram Protocol. And I'll describe it in a second, but let's look at chapter 4. I've always thought this was funny, and you can bear with me for 2 minutes. I think if you've gone through the phase of life called renting, you may or may not have people that have risked losing their deposit by breaking things like doors. And if in your rental experience, the dwelling is not like particularly new, and maybe it the way we do things in the U.S., maybe settled it on its foundation, and so it's no longer square or plumb. So the dilemma is you go to Home Depot or Lowe's or whomever, and you buy a door. The door is perfectly rectangular. The problem is the hole is not perfectly rectangular. The hole is whatever the hole is. You want your deposit back. You have to go. If you can tell, I generally teach this to an all-male class, and there I think is a substantial level of destruction to their apartments, as I'm told. It's not exclusively theirs, but I think that's where I borrowed the slide from the door square. In Plum, the structure is not. You have to stabilize the door with a bunch of these shims. You look carefully to the picture to the right. These shims are these prism-like pieces of wood that you just kind of wedge in there. You whack them with a hammer, you slide them in there, and the thing that was kind of shaky in the door frame, if you put enough of these shims in there, it will be solid. And so the shim is just there to fill the gap. I mean, in this case, you pound it in there with a hammer. Fine. That part is not really part of the story necessarily. The funny part of the story is that after you've done a bunch of these things, you have to get like bigger and bigger trim to cover up the mistakes. The shim only fills the gap between the frame and the structure. The shim only fills the gap between layer 3 and layer 5. That's 11 minutes of recording to get to my statement. Slide number 5. The user datagram protocol. Datagram is another word for packet, frame, segment, message, page, etc. Resides in layer 4, which is the transport layer that sits between layers 3 and layers 5. And to speak my language, I prefer the layers by their number. In that, theoretically, I think by the time, just out of my natural instincts, by the time we get to our module exams, I may just refer to these things by their number because they're shorter to type than their name. And I've already misremembered the name of TCP once already on a prior recording. Not enough to re-record it. TCP and UDP are instantiated, they live, they exist in all endpoint devices, PC, phone, etc. In one of my other classes going on right now, we talk a little bit about the Internet of Things. There are people with like the Ring doorbell, the Nest thermostat, Samsung wireless refrigerators. It's not uncommon to see a whole bunch of stuff in your home that can be internet attached. I don't even want to get into the notion of smart TVs, but I think the world has departed cable to go onto streaming devices or Netflix and have no device whatsoever. You are called the cord cutters, by the way. So UDP and TCP are in all the endpoint devices. Yes, the great big computers, and also the small devices as well. The UDP thing just passes messages from layer 3 to layer 5 in both directions. Doesn't think, doesn't dedupe, doesn't fix anything that's wrong. It doesn't look at the sequence numbers. It doesn't do error checking. It doesn't reorder, correct, seek retransmissions. If there are errors, it just passes them through. No metaphor for that one, unfortunately. As a consequence, it's like really fast because it does nothing other than copy a message from this storage area in RAM to another area in storage in RAM, and turns a flag on, turns a light on. It's really fast. It is the fastest mode of operation in which any network function can be operated. It's simply not true. It's simply not valid. We cannot promise error-free file transfers and not check for errors and duplications. The trade space for everything in networking gone wrong is delay. And so this thing is fast because it doesn't check anything. Let's say you needed to take some standardized test at some point. If you didn't care whether the answers were right or wrong, you could just put your pencil down and start circling answers in the test. Why even bother to read the test questions? So it, by definition, is the fastest way to get done. There are times in networking where we just want to see if we can get our stuff from this location to that location. And so we'll use this. We'll do things that are based on TCP. Sometimes we're sending things and we're going to maybe send 1,000 copies of the same thing just as a test. So for those of us in the testing mode of networking, it has its place. It's useful. I will say that on a project for a large government entity, we replaced their copper circuits with fiber optic circuits from here to there. And before we could, quote, put them into production, before we could actually use them, we tested our connectivity between the two locations using UDP-based test programs, and that was fine. And we understood at that point what the maximum data rate was when using UDP. We found a lot of interesting things that way. This is not off topic. When devices are set up wrong or the route goes through the wrong path, we were able to detect a really important class of errors by doing UDP-based testing. And it also became kind of the benchmark or the baseline for the following bullet point on slide number 5 was, then we tested it using the application. Then we used some other test utilities that resembled our applications and turned all the valves wide open in a TCP-based testing mode. Then we compared the results. The highest theoretically achievable highest achievable result would be the UDP performance number, and that would become the denominator divided into by the TCP-based realistic model for the application. And if it's basically the same number over the same number, then we knew that everything was going well. If we did not get exactly the same number, then we had the beginning of the testing exercise. And, the way I approached this was, we will not put this into use until we've tested this completely. So test for just basic connectivity, test for basic throughput, and then a test of throughput based on something that approximated what our desired application was. And you can't do this you can't test like that because it's very disruptive if you've got like real customers, real users, real subscribers on the network. So don't interpret end-to-end performance as indicative of the system, using UDP, qualifier using UDP, it's more complicated. So as we move off this slide, I will mention that an identifier is associated with TCP and UDP. We have assumed going into this class that you were comfortable with host names, which is host names and domain names. CNN.com is a domain. www.cnn.com is a host. OhioU.edu is a domain. www.ohio.edu is a particular machine. Email.ohio.edu, if it exists, is actually a machine. We're going to do cyber.ohio.edu. That'll be its own machine someplace. But, in addition to the machine name, and the machine name will get turned into a numeric address, each one of these TCP activities actually can have its own identity, that the email traffic will use its own channel number or actually port number. World Wide Web will use its own port number. We've allowed ourselves 64,000 different port numbers and reserved some of them for some well-known functions that will take place. We'll deal with this a little bit more before Module 2 is out, but we needed to add a little granularity to our problem. The modern computer is doing a lot of things seemingly at the same time. The duality principle says, of course, it's not doing them at the same time. It's doing one thing at a time and then switching over to the next thing incredibly fast. Well, it's also not enough to say I have one connection to a machine. Well, I have one physical link to a network adapter on a computer, but I can have many simultaneous logical connections going on to that computer. So that's not a bad way to wrap up our little lecture today, that the multitasking nature of compute in the internet age is manifest by identities for each one of these separate connections that the machine can possibly be doing at once. And we will do something fairly uncreative We'll give them a number between 1 and 64,000, and some things that we do common a lot, we'll just kind of associate a port number with them, and everybody in the internet will understand what those ports mean. Pretty good way to close the unit. The UDP thing is generally not used or implemented by people in the applications world. They are used by network technician type people to make sure things are working. And, on a happy note, what do we get out of this stuff? We get something about the port number going forward. Thanks for listening.